So on Wednesday, right, we started section 4.1 angles and their measurement. And right, we learned about the definition of an angle is, right, formed by two half rays, okay, at their endpoints. And you learned about coterminal angles with there are two measures, two ways to measure the size of an angle. One is degree measure, the other is radian measure. And any two angles that differ by an integer multiple of 360 degrees are called coterminal, right? They share the same terminal side when you draw the angles in the coordinate plane, okay? And that's important because we're going to be talking about the cosine and sine function today. And the cosine function, right, has the same value for coterminal angles. Then we learned about radian measure, okay? And angles measured in radians, right, are based on arc length, right, the length of the arc subtended, right, by two half rays. And right, we learned about coterminal angles, right, in radians. Any two angles that differ by an integer multiple of 2 pi, right, are coterminal. They share the same terminal side. And then we ended class on Wednesday starting to talk about how you can, an angle, the size of an angle measured in degrees, right? You can calculate what the size of that angle is in radians, and then an angle that is given in radians, we can calculate its size in degrees, okay? So, 1 revolution, right, equals 360 degrees. It also equals 2 pi radians, so 360 degrees is equal to 2 pi radians. And so when you divide both sides of this equality by 360 degrees, you get 1 degree is equal to pi over 180 radians. And when you divide both sides of this equation by 2 pi, you get 1 radian is equal to 180 degrees divided by pi. Okay. Now, when you're given an angle in radians, it doesn't have to have the number pi in it, okay? You can have an angle of 5 radians, right? Or 12 radians. But the only reason that pi keeps showing up in angles and radians is because there's 2 pi radians in 1 revolution. When you're measuring angles and radians, right? The circumference of a circle, right, is 2 pi times r. And so because the number pi is showing up in the circumference of a circle, that's why pi keeps showing up when we talk about angles and radian measure. Okay. So in example 4, okay, we're going to convert the angle 135 degrees to radian measure. Right. What's that angle in radians? Okay. Well, 135 degrees can be written as 135 times 1 degree, okay? And 1 degree is equal to pi over 180 radians, right? That's a fraction of a radian. Okay. So this can be written as 135 pi over 180 radians, right? And now because of the pi, right, whenever we see an angle with pi in it, we just assume it's radians unless we're told something different. And now you got to reduce 135 over 180, which reduces to 3 pi over 4. So the angle 135 degrees is equivalent to the angle 3 pi over 4 radians. Now on the exam, okay, all you would have to really do, right, is go from, you wouldn't have to include this step, right, go from here to here, right? multiply 135 by pi over 180, right? And then work to the final answer. I threw that second step in there just to clarify things. In example 5, we're going to convert 2 radians, and you notice that the angle 2 radians doesn't have pi in it. Right? You don't have to have pi, right, in an angle and radians. So we're going to convert 2 radians to a degree measure. Well, 2 radians is the same as 2 times 1 radian. And 1 radian is equal to 180 degrees divided by pi. Okay. And now, right, 2 times 180 is 360. So, 2 radians is equal to 360 degrees divided by pi, which you could write, sometimes it's better just to write it out in words, right? The fraction 360 over pi, and then write out the radians. Either or, doesn't matter. Okay. Any questions on that? Okay. The length of an arc. Okay. So we have a circle, right, with radius r. So I'm going to draw an angle with its vertex at the center. And so the distance, right, from the center to where the rays cross the circle, right, is r units. And so the angle between those 2 half rays is theta. Okay. So theta is in radians. Okay. And the length of this arc, we say the angle theta subtends an arc. It has length s. The equation for finding the length of that arc s is s is equal to r times theta. And theta has to be in radians. Okay. So in example 6, in a circle of radius 5 centimeters, an arc of length 3 centimeters, has an angle theta. Find the measure of the central angle in degrees and radians. Okay. Well, s is equal to r times theta. So if I divide both sides by r, I have s over r is equal to theta, or theta is equal to s over r. Okay. Well, s is 3, r is 5. Okay. So theta, right, as a decimal, right, is 0.63. You can write it as 3/5 of radians too. Theta is equal to 3/5 radians. To find the angle in degrees, we multiply it by 180 over pi, right? So this is equal to 540 over 5 pi, which is equal to 180 divided by pi, right? 5 goes into 540 108 times. So you need to put up the degree symbol, right, for write out the word degrees, 180 over pi. Any questions on it? Two acute angles are said to be complementary if their sum is 90 degrees. Two positive angles, right? Now acute, I said I have the word acute. What's the definition of an acute angle besides being acute? What? Less than 90 and greater than 0, right? Because you can have an angle of minus 400 degrees, right? So yeah, an acute angle, okay, is between 0 and 90 degrees, right? Greater than 0 degrees, less than 90 degrees. Okay. Two positive angles are supplementary, right? You notice it says positive. Two positive angles are supplementary, okay, if their sum is 180 degrees. Find an angle, that should be an angle. Right? Find an angle that is complementary to pi over 6. Well, what angle in radians is equal to 90 degrees? Yeah, pi over 2, right? Pi over 2 radians is equal to 90 degrees. So we're given, right, that one angle is pi over 6, right? So pi over 6 plus some unknown angle has to equal pi over 2, right? So this unknown angle is equal to pi over 2 minus pi over 6. Now you subtract one fraction from another, right? You have a common denominator. Multiply pi over 2, top and bottom, by 3. You have 3 pi over 6 minus pi over 6 is equal to 2 pi over 6, which simplifies to pi over 6. So the angle that is complementary to pi over 6 radians, okay, is the angle pi over 3 radians. Pi over 6 plus pi over 3 equals pi over 2, which is the same as 90 degrees. Find the angle that is supplementary to 83.5 degrees. Okay. So two positive angles are supplementary if their sum is 180. So we have 83.5 degrees plus some unknown angle has to equal 180 degrees, right? So this unknown angle is equal to 180 degrees minus 83.5 degrees, which is equal to 96.5 degrees. So 96.5 degrees is supplementary to 83.5. Okay. Area of a circular sector with radius r and central angle theta measured in radians is given by the formula A is equal to 1/2 r squared theta. So again, here's my circle of radius r. I'm going to draw an angle, right, at the center, right, with its vertex at the center, okay. Forms an angle theta. Theta is in radians. And the sector is like this. If you think of this circle as pie, okay, sector is like a slice of pie. That sector has area, okay? And that area is given by the formula 1/2 times r squared theta. Okay? Theta is in radians. What we're given for this problem, the radius is 3 millimeters, okay? And the angle theta is equal to 3 pi over 4 radians. So the area of our sector is 1/2 times r squared times 3 pi over 4. And now you got to do arithmetic, right? You got to do PEMDAS. So 3 squared is 9. 9 times 3 is 27. So we have 27 pi over 2 times 4, which is 8. And I don't think that reduces. Okay. You gotta have units. And so the area of the sector is 27 pi over 8 square millimeters. Any questions on that, ladies and gentlemen? Now, page 4, I'll let you read on your own. Okay. That's just right? Different terminology. You can read through that on your own. Okay. You don't need to read through it together. And then up here in this table, right, are common angles in both degree and radian measure, right? So the angle 0 degrees and 0 radians are the same. The angle 30 degrees and pi over 6 radians are the same. The angle 45 degrees and pi over 4 radians are the same, and so forth. And so you should be familiar with those common angles, right, in both degree measure and radian measure. So this homework is due Sunday night. Okay. 4.2, we learn about the sine and cosine function. Now, most of you if you were like me, okay, you learned about trigonometry in high school using right angles. Right, here's a right angle, right? Down here, this is 90 degrees. Okay. And these two angles are acute. This is the base, right? These two sides are called legs of the right triangle. Right, this is the base, right? And so the base has length A. Right? This is the height of the right triangle. It has length B. Then this is called the hypotenuse because it's the longest side and it's opposite the 90-degree angle, and it has length C. Okay. This hypotenuse, probably misspelled that. And then this is called the right? This is the angle theta. Okay. This is called the adjacent side because it's adjacent to the angle theta. And this is called the opposite side, okay, because it's opposite the angle theta. And then you're familiar with the Pythagorean theorem. A squared plus B squared is equal to C squared. And this works well, right, for acute angles. Okay? But angles, right, can be any size from minus infinity to plus infinity. Okay? So in your handout, right, points out originally the trigonometric functions were defined using angles in right triangles. A more modern approach is to define the trigonometric functions on sets of real numbers. Because in calculus and other subjects, right, we're interested in the cosine of 1 million, okay, not just acute angles. Okay? So in your handout here, okay, I'm going to reproduce this graphic, okay, step by step. Okay? So I have, right, we studied the equation of a circle, right, earlier this semester. Okay? I think it was exam 1 material, if I recall correctly. Okay? Had to complete the square to write the circle in standard form. Do you remember that? Good final exam question. Okay? And so here is a circle, okay, with its center at the origin, okay, in the coordinate plane. Okay? And this is actually a unit circle. What makes a circle a unit circle? What's the distinguishing feature of a unit circle? And the word unit kind of gives away. It has a radius of 1. Okay? So this is a unit circle. Radius r, right, is equal to 1. And we're going to be working with radian measure. Right? This is modern development trig functions. Okay, we use radian measure. Okay, and so the equation, right, for this circle in the coordinate plane is x squared plus y squared is equal to 1. Right? Remember, x squared plus y squared equals r squared if the center is at the origin, and r squared is equal to 1 in this case, right? Radius squared is equal to 1. Okay. All right. So now we're going to draw angle T. Now T can be a positive number, it can be a negative number. But I'm going to draw it as a positive number. And so here's the, right, you remember here's the initial side, coincides with the positive x-axis. Okay. And now here's the terminal side. And here's the angle T, we're calling it T, not theta. Okay. And the terminal side, right, passes through this point, okay, called P of T. And now the length of the arc, remember, radian measure is based on arc length, because the radius is 1, okay, the length of this arc is also t units. Because remember, arc length, S is, length of the arc S is equal to r times theta. If the radius is 1, r is a 1, then the length of the arc is just equal to the angle theta, okay? And theta in this case is replaced with t. So the arc length t is equal to the angle t, if r is equal to 1. Okay? So we have t is equal to 1 times t, right, which is just t is equal to t. Okay? Both the length of the arc and the angle, right, are t, length t, right? So this is the angle t radians, and the length of this arc is t units. Okay? Well, this point P of t here, right, it has an x coordinate and it has a y coordinate. Okay? The x coordinate we call the cosine of the angle t. Okay? The x coordinate of P of t is called the cosine of t, and we denote that with this notation down here, cosine t. See, oops. Right. This is cosine notation for the cosine of t. The y coordinate is the sine of the angle t. Okay. And the sine of the angle t, right, we denote with this notation right here. So this is the sine of the angle t. Okay. So instead of using right triangle trigonometry, okay, a more modern approach is to let the angle t be any size, okay, both positive and negative. Right, it can be this, right. There's no limit to how big it can be. There's no limit to how negative it can be. Right. T can be any angle between minus infinity and plus infinity. Okay. So that's how the cosine and sine function, right, are defined using real numbers. Okay. The terminal side of the angle t, right, crosses a unit circle at the point P of t, and the x coordinate for that point is the cosine of the angle t, and the y coordinate is the sine of the angle t. Any questions on that? All right. So the equation of the unit circle above, right, so I wrote on the board, is x squared plus y squared equals 1. And you know, in plotting, in graphing a circle, this circle, right, all the combinations, the graph is made up, right, the points on the circle are made up of all the combinations of x and y that satisfy this equation. Okay? And so values of x and the value of y, right, are between -1 and +1. On the far left edge, where the circle crosses the x-axis over here, this is the point -1, 1. Down here, this is the point 0, -1. Up here, this is the point 0, +1. And this is the point right here, is 1, 0. Okay. You know, those ordered pairs, right, satisfy the equation x squared plus y squared equals 1. So every point on this circle, right, satisfies this equation, and all these values of x that satisfy this equation, right, all the values of x are between -1 and +1, and all the values of y are between -1 and +1. And you can see the values of x, right, start here at -1 and end at +1 over here, and the values of y start at -1 down here and end at +1 over here. Okay. Well, because by definition, the sine of the angle t is equal to y, and the cosine of the angle t is equal to x, we can replace x up here with cosine t, and we place y up here with sine t. And when we do that, instead of x squared plus y squared equals 1, we have the cosine of t squared plus the sine of t squared is equal to 1. Now you can write this, you can write that, cosine squared plus sine squared this way, but it's common to put the square on the superscript of the trig function. So instead of writing cosine t in parentheses squared, we have cosine squared t plus sine squared t. And because x is constrained to be between -1 and 1, right? Cosine t is constrained to be between -1 and 1. And sine t, right? Because y is equal to sine t is constrained to be between -1 and 1. So the value of the sine and cosine functions are bounded. Okay? The cosine of an angle is going to be a number between -1 and 1, and the sine of an angle is going to be between -1 and 1. Okay? So this is an identity. It's true for any value of t. Okay? From -infinity to +infinity. Okay? Now I want to say one thing about the notation for the sine and cosine functions, right? And we talked about this with the natural log function. Okay? Function notation, right? I have f of t. Okay? T is the input to the function f, and f is its name. Okay? Well, the cosine and sine functions, right? They're just the name of functions like f, right? So we could write the sine of t in parentheses, just like we write f of t up here with t in parentheses. Okay? T is the input, and sine is the special name of a function. Okay? But just like with the natural log function, we often drop the parentheses and just write the sine of t without the parentheses. Okay? Just like we do with the natural log function. Okay? And the same is true with cosine. Cosine is the special name of a function. Okay? T is the input to the cosine function. So this is cosine of t, just like this is f of t. But because this is a name of a special function, we often drop the parentheses and just write cosine of t. So when you see this, right, you should be thinking this. When you see this, you should be thinking this. All right. So you flip over to page 2. At the top, we have an example, okay, of the Pythagorean identity on the previous page. Okay. So this says, right, so the angle 8, right, is in radians. So this is the cosine of the angle 8 quantity squared plus the sine of the angle 8 quantity squared is equal to 1. Okay. So I just put the angle 8 radians in for t on the previous page. And it also works for degree measurement, right? The cosine of 27 degrees squared plus the sine of 27 degrees squared is equal to 1. Okay. All right. Any questions on that? All right, another characteristic of the sine and cosine function The signs of the function values as sine t and cosine t are determined by the quadrant in which the point P of t lies. So when we talk about the signs of the function values, right, we're talking about positive versus negative, right? So if the point P of t, right, lands in the first quadrant, right, let's say this is the point P of t, lands in the first quadrant, that's where the terminal side goes through that point. You know, right, x is equal to cosine t, or cosine t is equal to x, and y is equal to sine t, right? You know that all points in the first quadrant, right, every ordered pair, x and y, in the first quadrant are positive, right? X is positive, y is positive. So if all points in the first quadrant are positive, right, if both the x coordinate and y coordinate are positive in the first quadrant, that means cosine t and sine t are both positive if the angle is in the first quadrant. Right? P of t is in the first quadrant. If P of t is in the second quadrant, right, the terminal side of the angle is in the second quadrant, okay, then you know the x coordinate is negative and the y coordinate is positive, right, for all points in the second coordinate. So that second quadrant, so that means cosine t is negative and sine t is positive if the angle if P of t is in the second quadrant. And then likewise, if P of t is in the third quadrant, okay, all points in the third quadrant, the x coordinate is negative, the y coordinate is negative, right? So that means both cosine t and sine t are negative, right? Have a negative value if the point P of t is in the third quadrant. And lastly, if the point P of t is in the fourth quadrant, all points in the fourth quadrant have a positive x coordinate and a negative y coordinate. So that means cosine is positive if P of t is in the fourth quadrant, and sine is negative if P of t is in the fourth quadrant. Okay. So in the exercise down below, right, and so you notice, right, you can, if you know what the sign of sine t and cosine t are, you know what quadrant P of t is in, what quadrant the angle is in. And so how we remember, okay, what quadrants sine and cosine are positive or negative. Some people use the acronym all students take calculus. All means they're both positive in quadrant 1. S means only sine is positive in quadrant 2. Now T, we haven't talked about this, we'll come back to this, means they're both negative, okay? This is actually refers to the tangent function. We'll have to come back to that. But just think of T as they're both negative, okay? And C, calculus stands for cosine. Only cosine is positive. Okay. All right. So in the exercise, if sine t and cosine t are both negative, then the point P of t and the terminal side of the corresponding angle, t radians, must lie in what quadrant? Which one is it? Yes, 3, right? Sine t and cosine are both negative. That's quadrant 3, right? Both x coordinate, y coordinates are negative.